Good afternoon or good day to cover all of your time zones. Welcome and thank you for joining us for our third webinar in our series, Enabling Effective Coatings Formulations to Improve the Durability of Assets, presented by Huntsman Advanced Materials. In a few minutes, we will introduce you to high-performance epoxy component solutions, which enable efficient and sustainable formulations to prolong the lifetime of construction and flooring structures. My name is Sara Fernandez, European Operational Marketing Manager for the coatings and construction industries, and I am pleased to be your moderator today. Let me introduce you to our matter expert presenting in a few minutes. He is Dr. Alex Bureau, our European Technology Manager for Advanced Materials, taking care of the specialty components portfolio for the aerospace, coating and construction, adhesives, and composites applications. Mr. Bureau has more than 15 years of expertise in the chemical industry. Before we start, let me remind you just a few house rules. This webinar will last about 1 hour, with enough time for questions and answers at the end. However, you may submit your inquiries at any time by using the chat option on your screen. Any question not addressed during the live event will be answered offline in the next few days. After the webinar, we will share with you the PDF file of the presentation via email. Also, please note that this webinar is being recorded and will be made available soon at the Huntsman website under the News/Webinar section. Should you be immediately interested in a follow-up discussion, please contact us via chat during the webinar or through your local sales representatives after this session. Alternatively, you can submit your inquiries at the Huntsman website via the Contact/Advanced Materials section. Finally, we would much appreciate your participation to our survey at the end, as your feedback is key to help us improve our next webinars. We would like to start by outlining the main differences between the content of our previous two durability sessions and today's one. At our first durability webinar in May last year, we provided insights on polymer design and kinetic features to support formulations of highly chemical and temperature-resistant coatings. At our second series back to October last year, we guided you through polymer design attributes with special focus on fast cure, adhesion, and carbon footprint for the development of highly sustainable and corrosion-resistant coatings formulations. Today, and following the specificities of the polymer chemical structure, we will address key infrastructure challenges like low emissions, UV light, chemical and impact resistance for a variety of surface and environmental conditions. What are the topics that we will be touching today? We will start with the general benefits and applications of the epoxy systems, followed by high-level science fundamentals on key features such as viscosity, crystallization, UV resistance, and hardness. We will continue showing our European Selector Guide for construction and flooring formulations, and this as an introduction to showcase polymer design features of our epoxy systems to enable efficient infrastructure projects and long-lasting mineral structures. We will conclude with a final selection of sustainable component solutions to enhance key formulation needs for construction and flooring applications. Let's get started with the chemical backbone of epoxy systems to explain the benefits and the broad range of construction applications in which they can be used. Firstly, what is an epoxy floor and why do we talk about enhanced performance of epoxy floors compared to concrete floors? You can see here on the top of the slide a selection of key properties that are improved by using epoxy systems for flooring, which Alex will be backing up in a minute with empirical evidence. An epoxy floor generally consists of multiple layers of epoxy with a depth of at least 2 millimeters that creates a high resistant, glossy and smooth surface that can be built in a variety of colors. When using epoxy technology to flooring solutions, its polymeric structure creates a remarkable strong bond that is able to withstand high temperatures, humidity, and abrasion exposure, providing 10 times more impact resistance than a concrete floor. That is why industrial sites, warehouses, and commercial buildings with heavy traffic rely on epoxy floors to ensure the durability of their assets and keep clean and safe conditions for workers, equipment, and inventory. Epoxy viscosity properties enable also more efficient and easy to apply formulations. And additionally, its flexibility enhances crack bridging resistance, which is required to adequately protect the substrate and accommodate movement, vibration, and impacts without cracking. So overall, epoxy systems provide superior, long-lasting performance for mineral structures and require little or no major maintenance over the years. At this point, I would like to hand over to Alex to learn the data evidence illustrated at the bottom of this slide. Please, Alex.
Thank you, Sarah. So in the table below, you can see the thermomechanical properties of a standard cement mortar versus an epoxy self-leveling or an epoxy mortar. The difference is visible when you look at the compressive strength, which is double in case of mortar. This basically reflects the way you can place on the floor. If the strength is improved, it is due to high elongational break of organic material versus mineral. Another advantage is the low water absorption of an epoxy and the faster cure of this thermoset material. Those advantages result in a better chemical resistance and a faster return to service. Let's start with the application flooring. In an epoxy floor, you need an hardener, often based on polyamine, and a resin. Generally, filler, pigment, and additive are also added. The formulated epoxy floor is tailor-made for the application, so it can be a primer, a self-leveling, a mortar, or a top coat. Specific properties, depending on the application and on the process considered, lead to different choice in the hardener and in the resin. For instance, waterborne solution requires specific choice of components. Also, when good surface appearance is needed under tough conditions like low temperature, high humidity, specific hardener should be used. It is generally the hardener which is key to the final properties, whether they are appearance, kinetics, or chemical resistance. Systems for other type of application are not so different than flooring. Concept is the same. You need an hardener, resin, filler, and additive. Process need to be chosen, waterborne or not, for example. You might be needing a fast cure for repair or a good crack resistance, for example. Often, in this type of application, the system is designed to achieve a very low viscosity, enabling the addition of large quantity of filler and higher strength. Many possibilities of hardener exist, and generally the challenge is to deal with fast cure, viscosity, acceptable pot life, and no VOC. So viscosity. Viscosity is a key parameter for most of the construction applications. To deal with viscosity, we have different resin to choose from, depending on the final properties you are aiming for. You can see on the graph, the viscosity varies quite a bit at low temperature, depending on the way the resin are designed. So low viscosity is often important to achieve a good penetration into the mineral substrate, which is slightly porous. It helps for good adhesion onto the substrate. And differences in viscosity are important also when you want to add more filler. Basically, it's easier to add filler to a low viscosity organic system, and then it's possible to deal with the formulation at low temperature. Another important parameter is the crystallization resistance. It is very difficult to reverse crystallization of chemicals. Actually, it's kind of impossible if you are on site. Because if you want to melt a crystal, you generally need to reach 70 degrees C while you are mixing the resin. So we have designed specific resin like araldite GY783 and or GY793 in a way to avoid this crystallization. Those two resins are generally fitting the self-leveling and top coat application. Okay, so we have explained how you can basically design an epoxy system using resin and hardener. And on the scheme, we present what is happening once you blend the epoxy and the hardener. So on the left, you can see the mix in the pots. You have then the open time, which depends on the quantity of product and the temperature. The application on the substrate is then represented, and the goal is to cure as fast as possible. On the top, you see an ideal system, fast to cure. On the lower part of the scheme, you can see when the surface is in contact with carbon dioxide, humidity for a long time. And the amine remains at the surface, and it leads to surface defect, which can be exudation of the amine or carbamation. The chemical scheme in the lower part of the slide explains what is carbamation. It's a reaction of CO2, of carbon dioxide, with an amine in presence of humidity, and this reaction is not reversible. So after cure, you have the case with no surface defect still on the top. And when you perform a water spot test, meaning leaving a drop of water for 1 hour and removing it, there is no trace visible afterwards. When you are in the second case of a bad cure, so the lower part, you see white traces which will remain for good. Different phenomena can be visible. White spot in case of water droplets, blushing of the wall surface in case of high humidity, or sticky, greasy surface in case of exudation. Basically, many defaults are possible which can be amplified at low temperature due to longer cure or unexpected high humidity. Hence, the choice of hardener is critical. So, and in this slide, we would like to explain what are the reasons and or solutions to diminish this surface defect. So, the goal is to favor the compatibility of an epoxy resin and of the hardener. By doing so, you diminish the risk of exudation. In the worst case scenario, resin and hardener will not be compatible at all, and you could get two-phase, so cure cannot really happen. So to help the compatibilization, we have designed hardeners in a way to support the miscibility with the resin. In effect, we modify the amine, and in some cases, we use plasticizer like benzyl alcohol. Low reactivity, high humidity, polarity of the amine can lead often to carbamation. And to circumvent this phenomenon, we use accelerators, special additives, and specific amines. We will discuss further in the presentation using appearance test, specific hardeners, and one additive actually. So now let's look at the final cured material. Once the epoxy is cured, you get a surface which is subject to UV light. It is clearly more pronounced outdoor, but indoor it's also possible as we generally have windows around us. Aromatic ring, which is a small hexagon represented, absorb UV light at 254 nanometer. This light is energy, which is dissipated in the material and leads to some degradation. In effect, it results in a yellowing and to an extreme to damage of the surface. Below, we have represented the chemical structure of a standard epoxy resin, and you can see the presence of those aromatic rings. And on the right side, some components often present in hardener, and here again, you can see the presence of those aromatic rings absorbing UV. So there is way to reduce UV absorption by playing with the epoxy molecule or amine we are using to design an epoxy matrix. So we have drawn different molecules, and the two left columns are aliphatic or cycloaliphatic molecules, which are not in principle absorbing UV. Generally, those molecules lead to lower viscosity, hardness, and reactivity. If lower viscosity is an advantage, lower hardness and reactivity are really a problem. To go around that, we can play with the functionality of the components, meaning how many reactive sites per molecule. So in the three columns, from the top to down, there is an increase in this functionality. It leads to higher viscosity and reactivity. It also leads to better hardness and better chemical resistance because the resulting cured material have higher cross-linking density. So in principle, it is possible to get a fully aliphatic or cycloaliphatic system, but you need to really take care that you get a good combination, curing well, and the resulting material hard enough. We will propose combinations which fulfill those needs after.
Thank you, Alex. Okay, let's leave behind for a minute molecular epoxy features and let's focus on less scientific information. As introduction to all the data that Alex will share in a minute on our specialty epoxy building blocks, I would like to present briefly the selector guide content that we have gathered specifically for construction and flooring formulations. The table you see here is meant to be a core portfolio matrix by product category on the left and key features on the top, addressing application needs to provide you at a glance with a possible selection of material combinations suiting your key formulation needs. We have streamlined even more this range with a summary that I will share at the end of the presentation, outlining our newest sustainable developments marked here in blue, like the CMR-free iodide DY31 multifunctional reactive diluent, the salicylic-free hardness Aracool 3077/1 and Ardo 2965/1, and the waterborne accelerator Aracool WB007. At this point, Alex will move on with key properties of the selected innovative products from the core range I have just presented, which are designed to lower the VOC output and boost the efficiency of your formulations for construction and flooring projects. So please, Alex, go ahead. Thank you.
Thanks. So on the efficiency subject, we wanted to start with waterborne. And generally speaking, epoxy chemistry is compatible with water. In this slide, we present a specific product, Aradio 3985. The product is 55% solid in water, solubilized in water, and can be used with 100% solid resin. Unlike what could be expected, it is possible to use it in a thick layer application. The water will be able to get out, and the mortar or the self-leveling will be porous or permeable, let's say. Unlike most of the other waterborne hardener, this one allows a visible end of pot life. It means you will see gel formation. For most of other waterborne systems, you will not be able to see that, and the risk is generally that the risk is to apply even when pot life is over. So on the left side, there is an example of a thick layer mortar, about 1 centimeter thickness, and you can see the simple formulation. On one part, the hardener is formulated with water and a defoamer, and the second part, it is a pure araldite PY304, formulated with a blend of different particle size quartz. It helps to ensure good packing and the good mechanical properties of the mortar. Generally, the advantage of using waterborne for this application is to reduce the viscosity, allowing a large amount of filler and to ensure good wettability of the substrate. It's also much easier to clean the equipment as you can do it with water. So on the right side, it's a self-leveling system. It's about 5 mm thickness. In this case, the resin is araldite GY257. This resin is not formulated here. The hardener is, with a specific process allowing the good incorporation of all the elements. This self-leveling is breathable, meaning that vapor can go through. You can then avoid blister in case humidity would come up from the ground. You get a matte appearance, self-leveling with a very good adherence onto the substrate. Generally, still on the waterborne subject, generally waterborne systems are not so fast to cure, and often there is a demand to speed it up. But unlike traditional systems, standard accelerators do not work very well, as those have to be added at the third part. So this new Aracool waterborne 007 is water soluble, so it's mixable with any waterborne hardener. It maintains on top of the acceleration a good flexibility, and it has a good EHS profile. When you look at the graph on the right, you can see on the left side the pure Aradur 3986 Araldite PZ 756-1 system. And going in the right direction on the graph, we substituted Aradur 3986 by the Aracool waterborne 007. They have similar H plus equivalent weight, so you can do that. You can see with the continuous line, the drying time at 23 degrees in orange or at 10 degrees in blue. The dashed line are the visible end of pot life. The system Aradur 3986 PZ756-1 has no visible end of pot life. And you can see that with 5% substitution of the hardener, it allows already the visible end of pot life, which is really positive for a waterborne system and because it avoids the mistake of the applicator. The acceleration is really visible at 10 degrees from 6 hours down to 2 hours if you would use the accelerator 100%. At 10 degrees, you get a visible end of pot life around 50 degrees, either at 30% substitution or 100%. At room temperature, the drying time can be divided by 5 when using 100%, but the duration is also reduced tremendously, about 20 minutes when 100% are cool. So, as usual, an accelerator reduces the drying time, but also reduces the pot life. And the optimization needs to be found depending on the process and the application type, let's say. So here we have an example how to use this new Aracool waterborne 007 as a drainable mortar. So we did a simple formulation presented here. And so basically the standard waterborne resin Araldite PZ 756-1/67, the pure Aracool waterborne 007, and some grits. The mix was done quickly, and after 30 minutes, the product was hard, with still a good level of flexibility, helping the adhesion between the small stones. No? Due to large porosity, water is going through, as I'm trying to show you now. Voilà. Here, another example of use of this new accelerator, and in this case with cement. So the principle is epoxy cement concrete, and basically cement needs water to react. So by using waterborne epoxy, we can introduce in the cement some organic epoxy thermoset, which brings some additional properties to cement, like strength. Here, the Aracool waterborne 007 also brings some acceleration to fasten the curing. On the left part of the table, our reference, cement, just water, sand, and cement. And to this, we add the epoxy Araldite PY22783 and the Aradur 36. Araldite PY22783 is a low viscosity emulsifiable epoxy resin. And what we can see in terms of effect is already with Aradur 36, you get a faster workability or settling of the material. In the last two columns, we are adding or substituting completely Aradur 36 by Aracool waterborne 007, and you can see that reaction is accelerated. So the new Aracool waterborne 007 allows to create a faster epoxy cement concrete. It improves flexibility and adhesion and avoids cement latence. Viscosity can be adjusted depending on the quantity of cement and the water used, of course. So, in previous slide, we did look at waterborne TIMA or system and our new waterborne accelerator. And on this slide, we propose our fast cure hardeners, VOC and SVHC-free, which can be used for many applications. So repair mortar, but also potentially as co-hardener to accelerate any slow curative. On the left graph, in the x-axis, you have the pot life at room temperature, and in the y-axis, the thin film drying time at room temperature with Araldite GY783. The size of the bubble is proportional to the mixed viscosity. On the right side, or on the right graph, it is similar concept, but at lower temperature. So here the drying time is at 5 degrees and the pot life is at 10 degrees. So it's clear that Aradur 33641 is the most reactive, either at room temperature and at 5 degrees, but the mixed viscosity is high. So to me, it's a great product to be used as a co-hardener. Aradur 2992 is very low viscosity and great reactivity-wise, but the result at low temperature show exudation when used in a thin film application. Aracool 3077-1 is a very good compromise. It is low in viscosity, it has relatively long pot life and dry pretty well at 5 and 23 degrees. It is a very good choice, for instance, for a zero VOC repair mortar system, as I present on this slide. So here we focus on mortar. Generally, the hardener needs to be low viscosity, enabling a very high filler loading, about 90%. Having this loading allow high strength and high hardness, as well as good chemical resistance because of the organic part. For fast repair, a fast cure hardener is generally preferred. And here the Aracool 3077-1 in combination with standard low viscosity Araldite GY783. This is our example. You can see on the right the simple formulation with different particle size sounds, enabling a good packing of the filler. So generally, for mortar, the goal is to deal well with viscosity, and for repair, with fast reaction. Lots of different hardener can be used for this type of application. Why lots? Because here the appearance is less of an issue than with self-leveling application, as we are going to see on the next slide. So on this slide and on the next one, we want to focus on 100% solid epoxy self-leveling hardener, and potentially also for top coat or thin coat. Those hardeners are designed in a view of very good appearance, and generally speaking, goal is to get a certain reactivity, either in cure and in gel time. They vary also in their viscosity, which enable, when very low, to add more filler and still have a very good flow, ensuring leveling. As you know, for these applications, the final appearance is key, and the hardeners are made in a certain way to achieve good appearance. Along the year, many accelerators used in those hardeners became substance of very high concern. And we have been always very proactive to anticipate those changes. Also, you can see the -1 or the -2, which means we either removed phenol, bisphenol A, nonylphenol phenol, and more recently, the salicylic acid. On the graph, we have mapped 7 of those hardeners. The x-axis gives an idea on the gel time at room temperature, while the y-axis gives an idea on the hardness development at 10 degrees. Size of the bubble is proportional to the viscosity as usual, here at least. H plus equivalent weight mentioned relate to the mix ratio. Hence, if H plus equivalent weight is 95 grams per mole, you need 50 parts of hardener for 100 parts of standard resin by weight. We can clearly see that curing development is linked with the gel time. So depending on the needs, the right compromise must be found. And another parameter in this range of products is water spot resistance and appearance. And we have tested those parameters on the next slide. So the same hardeners shown before have been tested at different curing temperature, 5, 10, and 23 degrees C. This is mentioned in the x-axis. Each column represents one product. The higher the bubble is, the better water spot resistance it is. The size of the bubble relates here to the surface appearance, and the bigger, the better. To give a mark on those parameters, we have a scale for each test. We have run those tests in parallel, so the appreciation of the result is reliable. Based on the previous slides, the faster hardeners are on the left and the slowest on the right. You can immediately see that the Radio 53-1S is very reactive, but is not the best for water spot resistance nor for surface appearance. Generally, for appearance, Radio 46-12 gives the best result at all temperatures due to the good reactivity and best water spot resistance. In the other hand, if the product used will be in a warm area, the choice might be about having a long open time more than curing at 5 degrees. So in that case, Aradur 2963-1 works very well, as it is not too fast, it's low viscosity, and has still a very good appearance at room temperature. Generally, in this subject, there might be other needs, so like mix ratio or being low yellowing. And at the end, it's all about optimization and priority, I would say. Here, we wanted to speak about this product because one easy way to improve appearance or water spot resistance is to use an additive. And this additive is a modifier DW1765. It helps to reduce the surface defect. It also helps for intercoat adhesion when an additional layer is added on, and for scratch resistance eventually. On the graph, you can see the effect on a very bad reference with bad water spot resistance at 5, 10, and 23 degrees. Adding 2.5% reduces considerably the surface defect, and with 3.5%, the surface is kind of perfect, even at 5 degrees. So the modifier 1765, I would say it's a good way to improve a formulation without changing it. So without changing hardener and resin, it's more like a drop-in. That's the advantage.
Thank you, Alex. Let's give Alex a well-deserved break and allow me to open up our second part of this presentation. So far, in the previous slides, Alex has showcased how to empower faster return to service through more efficient and easy to apply formulations. In the upcoming second part, he will focus on the longevity as ultimate enabler of sustainability. You will learn how our component solutions help to ensure that construction structures withstand external aggressions without deteriorating for a longer time. Before handing over to Alex, let me please remind you to submit any inquiries you may have so far through the chat menu on the top of your screen, so that we can address them at the end of the presentation. Also, please note that we will post in a minute in the same chat feature the link to our short survey, and would much appreciate if you fill it in before you leave. It will really take you only a few seconds, and if you let us know how we did it today, we will work on trying to do it better next time. So, Alex, I hope you are ready for the last run. Please go on.
So, durability. So no surprise that primer comes first. So I'm going to speak about primer a bit. So generally, primer is here to reinforce the surface of a concrete and also to ensure the better adhesion of the next layer. So in this part, we focus on primer for marginally or freshly prepared surface with no need for surface pretreatment. So this range of products is designed to provide an outstanding adhesion and a good reinforcement of the concrete. Those products are made in a way that they even cure well underwater. And this ability of curing underwater enables the application on green or fresh concrete. Basically, no need to wait for the full cure of the concrete. It is possible to apply the primer as soon as you can work on the new concrete. It also allows to seal the concrete so it can cure without water evaporation, which helps for the quality of the concrete afterwards. So the first generation of product, Aradur 450 and Aradur 450-1, was designed with some benzyl alcohol, which is today considered as a volatile organic compound. So the 450-1S is faster than the 450. And the second generation, VOC-free Aradur 3282-1, is slower but gives similar good adhesion property. And the Aradur 2745, also VOC-free, is much faster, as you can see on the graph on the left. On the right table, a few data on the bond strength to concrete. Basically, with a pool of tests, we can see that the failure is not adhesive, but mostly cohesive, within the concrete, proving the outstanding adhesion of the system onto the wet concrete. Here, another application called crack bridging layer. So often when people think about epoxy, they assume it will be very hard, but actually it does not to always be that way, to be hard. So the few hardener presented here have been designed in a view of high elongational break. With these systems, it is then possible to reach up to 300% elongational break, a bit like a rubber. Application can be flexible layer to absorb movement from the ground. And in case of crack, the flexible layer can absorb the crack or the energy of the crack to avoid the propagation to the surface. You can see an example on the picture where the top layer is not damaged while the under part is completely cracked. So more generally, you can create with those products waterproof membrane or flexibilized system which are a bit too rigid. Here on the scheme, or the graph more, you can see the three products discussed before. And on the x-axis, you can see the gel time, and on the y-axis, the elongation at break. The size of the bubble is proportional to the viscosity. If Aradur 70 gives up to 300% elongation, the viscosity is high and the reactivity extremely low. So the two other products, Aradur 75-1 and Aradur 3275, are still giving a good elongation at break around 130%, while reactivity is more in an acceptable range. Aradur 3275 is also very low in viscosity, but what we observe is that toughness is better with Aradur 75-1. So if you want to put filler, of course, Aradur 3275 would be better, but for toughness, 75-1 is more interesting, I believe. Low yellow. Here, as we've shown before in the first part of the presentation, the epoxy systems are subject to UV exposure, which lead often to yellowing. As discussed earlier, it's possible to minimize the yellowing when you choose the right building block, not aromatic, but it's also important to tune the other parameter, reactivity, and so on. We find two different applications for low yellowing. The first one would be with thin film application, and it is then critical to get a good reactivity, otherwise you would have a dreadful surface. And then there is no point then to be low yellowing if it's a bad surface. A second application can be like the river table on the second picture on the right, where you have a very thick layer casting up to 15 centimeters, for instance. In that case, it's critical to limit the heat development, or also called exotherm, when the epoxy cures. Hence, you need a very low reactive system. And why no exotherm? Why we want to avoid exotherm? It's also because exotherm leads immediately to a color development in the epoxy system. So it's also important for this thick layer application to avoid exudation, because that would not be nice neither. So in this slide, we have gathered the building blocks which are relevant for low yellowing application. On the left side, the curative, and on the right side, the resins. Viscosity is proportional to the bubble size, and color intensity to the UV absorbance. So in effect, the deep greens bubble are standard reference, which are not especially low yellowing. In the x-axis, we have put the reactivity, and in the y-axis, the impact on hardness after cure. For instance, if the combination araldite DYC with Aradur 53-1S will cure okay and be relatively low yellowing, the product will be soft, which maybe not so great. If the combination Epaloid 5000 with XB 3403 would be low yellowing, for a thin film application, the appearance would not be good because reactive would be too slow. So here, a good combination for good hardness, low viscosity, and low yellowing could be Aradur 2317 with araldite DY31. And on this slide now, we show the result of different systems based on different building blocks. In general, the tests were done in a view of thin film application. So on the left graph, you can see the yellowing index, and on the right graph, the gloss evolution versus time in QUV chamber. This test, this QUV chamber is an accelerated test. And if we compare with results behind the window, they follow the similar trend or the same trend. And generally, we have seen that 15 days in QUV chamber is about equivalent to 1 year behind the window. In green, we have the reference system, Araldite GY7H3 with Aradur 2965-1. After 2 weeks, the system is yellow, as you can see. And you can also see the loss of gloss. It means the surface is damaged and there is potentially extraction of the plasticizer, leading to a matte effect. When replacing the resin GY7H3, which is aromatic, by Epaloid 5000, which is not aromatic, and keeping the same hardener, we can see that the yellowing is less pronounced. Nevertheless, after some time, it also becomes yellow because of the hardener. So, as expected, the best system is when you use Aradur 2317 with Araldite DY31. We cannot guarantee that it will never yellow, but it resists about 100 days in the QUV chamber, and we then see the loss of gloss, also the degradation of the surface. It is the blue curve. So Araldite DY31 seems to give slightly better results than with the Epaloid 5000, which is the orange curve, and it's due to the higher hardness of the system when you use Araldite DY31 versus Epaloid 5000. So as a conclusion of these parts, I would say that epoxy system can be relatively low yellowing. Maybe not no yellowing, but low yellowing is possible. Thank you. I think I hand over to Sarah.
Thank you, Alex. So, as anticipated in the introductory part, when showing our selector guide of core products, I would like to finish today's presentation with a streamlined overview of our selection of key sustainable epoxy components. Starting with the SVHG-free or zero VOC hardeners on the left-hand side, all of them are designed to address a broad range of specific and critical application conditions. On the right side, we showcase our two newest eco-conscious innovations, our CMR-free multifunctional reactive diluent Araldite DY31 and our Aracool WV007 accelerator for waterborne systems. Finally, although not new, not less relevant, our modifier DW1765 additive, relevant for its ability to boost impermeability and scratch resistance. And with this, we conclude our presentation of today and would like to open up for your questions. If you allow me, I would like to start maybe down to top with for practical reasons, just so we will get to all of them, hopefully. So we have here the latest one, I guess, yeah, I think so, it's from Venkatesh, whether we have a similar modifier for a non-waterborne system to improve the carbamation resistance. Would you be able, Alex, to address this question?
Yeah, sure. But actually, I guess the question was about the modifier 1765.
I think so, yeah. I don't think it would be the waterborne accelerator.
So this modifier is actually for solvent-free and not waterborne system. And so in principle, it does really improve the carbamation resistance. So I don't have similar modifier for waterborne like the DW1765, but it works for solvent-free product. Solvent-free solution, sorry. Very warm, yeah.
Please, Venkatesh, in case we had misunderstood your question or you would like additional clarification, don't hesitate to enter your question or your clarification again. So the next one is coming from, well, I will follow again the logic and start with the latest one that we have got from Hisham. What is the difference between exudation and blushing? Alex.
The difference is that exudation is basically, as I try to explain, you really have an incompatibility of the resin and the hardener, and at some point upon the cure, you kind of press the amine towards the surface. These amine generally remain as a greasy surface, which is the amine. It's what we call exudation. After, this amine can become white when it reacts with carbon dioxide, and then that's called carbamation. So what exudation, let's say it's a bit extreme, while carbamation is something which is really depending on the humidity, and you can have exudation without carbamation because you don't have high humidity. But exudation, it's really because there was something wrong during the cure, while carbamation can occur surprisingly because the humidity was 80% and generally it's 50, something like that. But it's not really the same. The carbamation is something reversible, irreversible because it's you create this white stuff or blushing. While the exudation, in principle, if you are pretty lucky, you could even think about washing it off. I don't think it would be great, but it's not necessarily leaving something white.
Thank you, Alex. Next one from Hisham about the building block GY783 and R75/1, whether it gives long-term flexibility and elongation. Means no drop, little drop in elongation and flexibility. Would you give some insights there, Alex?
I mean, it's in principle there should not be drop in elongation, but it's difficult to say that there will be no drop at all. If you think about a rubber, a standard rubber, generally you put that under the sun, and then if you come back 10 years later, your rubber has become brittle because there was a UV light, and generally you have a radical transfer, and then you start to kind of cross-link your rubber. In case of our product, there is less chance of that because there is no polybutadiene in our formulation. But I will not say and not sign with my blood that there will be no loss of elongation at time. But in principle, it's not. These products are not generally not under the light or under the UV. They are intermediate coats or layer, and they are not subject to a lot of UV. And I would say there is not massive drop in flexibility or elongation at break.
Thank you, Alex. I have seen new questions coming in, but please allow me that I finish going up with the questions. We will come back in a minute to the one posted from Bagul and Kimika Fine, but just so we'll come back in a minute. So we have Adam asking whether we can enhance somehow surface properties like orange peel or cratering using the modifier DY. Sorry, DW1765.
So there is different kind of surface defect. I would say the DW1765 is really for the carbamation resistance because it makes your surface a bit more hydrophobic, so water repellent, and helping for this carbamation resistance. You help for the recoatability because if you have a carbamation, then you have a fragile intercoat adhesion for the next layer. In principle, I would not say that it's not helping for the crater formation But it's not the main goal, and you know, there is other additive in the industry that are not in our portfolio, which do that pretty well to reduce the crater formation. This product most likely help, but that's not his first feature, I would say.
Thank you, Alex. So we come now to the question from Mikael, whether the Arado 2965/1, the one we have presented, salicylic acid free, sorry, whether it contains benzyl alcohol.
Yes, it does. Yes, it does. So Aradio 2965-1 is actually almost the same as Aradio 2965, which is a product known, and we just wanted to replace the salicylic acid being proactive, and the product has exactly the same property than the previous one. And yes, it does contain benzyl alcohol, and generally we said that the property having replaced the salicylic acid is actually a bit better in terms of less yellowing. But yes, it contains benzyl alcohol.
Thank you, Alex. So next one from Ali. Well, actually, is the first one on the list. So we will now start to go top down. Ali is asking, well, you can see it. One of my choices to reduce the cost of my epoxy product is to choose an activator with low amine hydrogen equivalent weight to decrease the amount used. This is idea can be a solution. The price of an activator is affected with this solution. So would you have some comments to that, Alex?
Yeah. So yeah, I understand the question. So basically, the concept is to say that by using a low H plus equivalent weight, you need to use less hardener, and generally the hardener is more expensive than the epoxy. So it allows to reduce the price of the whole system. I see the point. It's possible and it's existing. So we have product called Aradur 847, which is a H plus equivalent of 75. Yes, I think so, or 85 or 75. No, 75. So in this case, you can only use 40 parts instead of generally 50 parts of hardener versus resin. I mean, I'm not sure I understand the question really. It's a general comment. I believe you will always lose in surface appearance at some point if you really reduce, if you have too low H plus equivalent weight. That will be my comment. If you go lower than 75, it starts to be a bit difficult to have this good compatibility with the resin. But I'm not sure I got the question.
Thank you, Alex. So please, Ali, if you feel like you need more clarification, don't hesitate to submit again a more precise question regarding your concerns. So we have, before I jumped to the last question, so we had one. Here it is, how we can increase the addition of the waterborne system composed by the araldite PZ 3961 and the aral 3986.
So araldite PZ 3961 is not really a product to be used in the construction area. It's a solid epoxy resin dispersed in water. So it's a very special product which is generally used for anti-corrosion coating in combination indeed with 3986. The adhesion is very good on metal and for some flexibility reason. In construction, it doesn't come to me as the first choice because you will have still a solid material. So to improve the adhesion or I don't see any way onto a concrete because one way will be to reduce the viscosity and to add more water. But at the end, then you will reduce your solid content onto the surface, so it will be less solidified. I don't think in the view of a construction application, it's a good choice. For coating, I think the adhesion is pretty good, kind of the best. So to improve further this adhesion, you can consider epoxy silane maybe, but I'm not sure it's the right way.
Thank you, Alex. We have got clarification to the previous question from Ali. So it was meant to be about using pure amine with low AHEW instead of formulated hardener like IPDA, Jeffamy. I don't know, Alex, if this gives you a better idea of what he was trying to find out.
Yeah, okay. So, I mean, so everything which was presented today is if you try to use, let's say, as you said, Jeffamine or IPDA or any free amine, if you use them like that with a standard epoxy resin, you won't have a good compatibility. So you will have a tremendous effect on it's called exudation. There is way to go around this problem, but there is not so much you can do. And that's why there is the existence of the hardener I have presented today, especially for surface appearance, is that generally you will have an incompatibility and you will get a very bad surface appearance, especially if you can't post-cure or cure. And in cold condition, it's dead. It's not going to work at all. That's what I said in the first part of the talk, is how do we play? What we are doing is actually modifying those amine. We are adding plasticizer like benzyl alcohol sometimes. We are adding accelerator, and we are choosing the amine in the right way depending on the condition, and we are blending amine also to favor and to go around problem like exudation, like carbamation, and also to avoid sticky surface and things like that. But I can guarantee that if you use a product like IPDA Pure, you will get an horrible surface, even if it's 40 degrees outside. That's why those products exist. So meaning 2965-1, 46-2S, all the 7 products I presented. There is more than those, and generally you always need to play. You need the technicality of making an hardener versus a free amine.
Great, thank you, Alex. It looks like it has been clarified according to Ali's input. And yeah, it also looks like we are just on time. We have addressed all the questions we had, and it's time to close for today. But before we do so, we would like to thank you all again for your participation, and we hope that we could raise your interest. As I said at the beginning, for further follow-up discussions, please get in contact with us via our sales representatives or our Tagsman website under the contact/advanced material section. And before you leave, please remember to take part in our survey that we have posted in the chat. Of course, if you like to stay up to date on our news, you can also follow us on social media. So thank you very much again for your time, and we look forward to seeing you at our next durability webinar session. Stay safe and wish you a very nice rest of the day. Bye. Thank you.
Thank you. Bye.